Good afternoon to everyone. We still have people coming in, so maybe we'll use a few minutes to introduce ourselves to one another. And as you might have guessed, this is a talk about data, so let's just use that. With a raise of hands, who here uses data on their day-to-day? Okay, so that's almost all of you. It's probably all of you, right? It's kind of unavoidable in software. There's some software that doesn't use data, but most of it does. But trickier question. Who of you is willing to define themselves as a data professional? So that means that your day-to-day revolves around data. That means you're a data engineer, you're a data analyst, you are a data infrastructure engineer, data scientist. Okay, not that many hands, great. So this talk is for all of you, right? It's primarily for the first part that raised their hand, but also for the second part. I hope there will be some of it for you as well. But last one just for kicks. Who has the term big data in their LinkedIn profile? Okay, if you take just one thing out of this talk today, right after this talk, go to your LinkedIn profile, add big data there. Trust me, you'll have so many recruiters approaching you, so much more money. It's just amazing, right? So I got to know all of you. Might as well just introduce myself as well. So my name is Josef Goldstein, and I'm leading the group building Wix's BI and data engineering platform, or in my LinkedIn profile, big data platform. Right? We talked about it. So this is obviously a talk about system architecture. So trigger alert, there's going to be a lot of diagrams in this one. I apologize. And we are going to talk about architecture, most specifically data architecture, or as I like to call architecture, you know, the arts and pseudoscience of being able to tell the future and build a system based on that, right? So it's a joke, but you kind of understand what I mean by that. And when we talk about data architecture, we obviously talk about the data parts in our system architecture. But I like to split the world into two. You're kind of going to get to know which part of this I am talking about. The operational plane of our data architecture and the analytical plane of our data architecture. So the operational plane is, you know, the databases where we hold the data that we use to run our microservices, our general business, right? There's a lot of talks about this here today. This is not the focus of this talk. What we are going to talk about is the analytical plane of our data architecture, right? And this is going to be the focus because this is not being talked about a lot. And it's becoming increasingly an important part of any serious system out there. And it's actually one of the most interesting parts of system architecture when you think about it. But again, not as known, right? There's a lot of mysterious stuff about that and the term big data. Before we start, the second term that I want to kind of unpack is the term evolution, right? So like it says, data architecture evolution. I truly believe that system architecture, software architecture, and data architecture as well are an exercise in evolution, right? So I joked about the pseudoscience of telling the future, but the reality is that usually we only know so far into the future where the business is going, right? Maybe know 2, 3 years. So when we are architecting our systems, we are making bets. We are making bets in evolving our systems in the best way possible based on the knowledge that we have right now. So actually, the exercise of architecture is the exercise of intelligent evolution. The problem with that, sometimes evolution goes wrong. And when it goes wrong in architecture, it is expensive, right? That kind of makes sense. The stakes are higher. But when we talk about data architecture specifically, the stakes are even higher. Now, why is that? Data is by definition persisted and stateful. Anything that is persisted and stateful is much harder to change, much harder to evolve. Now, if you want to kind of get the intuition to why that is true, imagine a stateless microservice, right? And you decide you need to evolve it into the next stage. The business changed. What do? Go to the ABI/v2 and then implement it. Let's say you made a mistake. What do? /v3, and then you create the new implementation, right? Fairly easy. Now let's talk about data. Let's imagine that you have a petabyte of data sitting in a certain database in a certain format. Now you want that data, different database, different format, right? That is expensive, that is hard. And if you made a mistake, well, you just have to do that again. So being able to evolve data architectures is not only interesting and important for modern systems, it's also something that's tricky and mistakes can cost you a lot. So this is the exercise that we'll be doing today. We're actually going to be doing like a tiny workshop with playing around with architecture, right? So imagine we're all together in the office. It's a very big office. And we're just scribbling the architecture of that system that we're building right now. And we're slowly asking ourselves, where do we need to evolve it next? Now, how would we usually do that? We would use a whiteboard, that is right. The nice people from NDC didn't let me bring a real one, so we will use that one. They also said I can't use markers on that for some reason, so we'll just use what we have. Okay, system architecture, day 1. Any surprises there? No, I don't think so. So, obviously, not all systems look like that. They're day 1, right? Today, everything has to be microservices and whatever, right? But ideally, most systems start here. And that raises the first question. Where is our data architecture? Anyone want to take a stab at that? We have a database. This is not a trick question. We have a database. It's right over there, right? It's right over there. And at this point, we actually don't have an analytical data architecture, an analytical data plane, right? Everything is there. That's the data that we use to operate our system. That's pretty simple. When do things get complicated? They start to get complicated when people ask all those gosh darn questions. They're bastards. What kind of questions are we talking about, right? So that can be, product manager coming to you and telling you, look, I want to know what are the top 5 countries we're getting traffic from. Or maybe we have someone in the company that wants to see how our funnel looks, right? Where do people drop off? Or maybe just your boss wants some report, right? And what is unique to all these questions is that they are analytical by nature. And analytical questions are questions that spend large amounts of data and do things that are computationally intensive. So for example, in order to answer the question of what is our top 5 countries in the past month, we will need to scan all the data from the past month and aggregate it based on a country. Now, doing things that scans a lot of data and are computationally intensive on our operational database, not a good idea. Anyone try to do that? Yeah, that's when you get the call that says, my site is slow, please stop whatever it is that you're doing there in engineering, right, from your salespeople, right? You don't want to be there, right? Because again, those questions, those analytical processes are very computationally expensive. We don't want to adversely affect our operating system. So what do? We don't do that? Of course not. The manager, our boss asks for a report. So what do we do when we have a problem? Anyone? We solve it. But how do we solve it?
Buy a bigger computer.
Buy a bigger computer. That's always good until the CDO calls. So when I have a problem, I write a script, right? You have a problem, you write a script. That's so simple, right? And you write a script, and ideally it's going to be written in a language which you will not be able to maintain later. But I'm just building it one time for my boss that asks for the report, or just a small table so the product manager can play on the side with the data. And what that script is actually going to be doing, he's going to go to our operational database once in a while, and he's going to take the data that we need to answer those specific analytical questions, and he's going to smush it, aggregate it, and he's going to write that into an additional database in an aggregated form in a way that's built to answer all those analytical questions. Right? And if we're smart, maybe we'll even slap like a BI tool on top of that, so the product manager can play around with nice graphs and everything. But what we've essentially built here, and we probably don't call it this way at this point, is our first data warehouse. And anyone here heard the term data warehouse? Cool, awesome. So most people don't call it a data warehouse at this point, right? Because it's not that premeditated. But it essentially is. We have actually split our data architecture into 2. The operational plane and the analytical plane, right? One is our operational database, the other one is the data warehouse. The other thing that we've done is creating a new side job for you. That's right, because no one obviously planned this. This script is now something that you need to maintain for the rest of your life. Now, things don't stay simple for a very long time because we have split our architecture into the operational plane and the analytical plane, right? But the business continues to move. the operational plane continues to move. And at some point, there's going to be a pointy-haired architect, and he's going to look at the system and he's going to say, monoliths? Who's building monoliths this day? We need to go microservices. And if you listen to Martin Fowler, you would know that when you build microservices, each microservice need to have their own segregated domain-bound database. Right? Everyone knows that. I see nods. Good. Right. What this also means is that your magical script and that magical data warehouse that maybe you don't call a data warehouse yet is the only place where you can cross-reference data across all domains of your product, which is very, very cool. What this also means at this point, that this is your full-time job at this point. This is actually a really good time to kind of contemplate. Maybe you want to change your job title, go to LinkedIn, remember, big data, stuff like that. Now, jokes aside, this is a sustainable architecture. And that is a term that I will be using several times during this talk. And I actually mean that, right? There's no one way of architecting analytical data. And that's super important that you understand that, right? And this is a sustainable architecture. That's sustainable for companies and businesses that, well, they're small. They don't have a lot of data. Or maybe they're just not data-centric. They're not generating a lot of data. And they just really need those few reports for your boss to just get by. And that's fine. But things don't stay simple for a long time. Right? That's the reality. And there are problems with this architecture. Can anyone spot the problems in this architecture? It's a real question while I take a sip. I heard real-time analytics. Sir, you're getting a 1+1, but I'll meet you in 15 minutes into the talk. Anything else besides the very advanced stuff? So let's start with the beginning, right? We said the business moves. And that pointy-haired architect might look at our architecture and say, look, relational databases, it's a thing of the past. It doesn't answer our business needs. We need to go NoSQL. And when we go to NoSQL, the data is no longer relational. All the stuff that we've built slowly breaks apart. And you're going in and out of meetings because, you're the script kiddie guy that makes sure that we have data for the bosses. And you hear new names of stuff, and you don't know if that's a new database or a Pokemon. What you do know at this point is the things that you're building are breaking, and your boss is angry, and your product manager is angry because that stops working. Now, that's funny, but let's kind of do a deeper analysis of what just happened, right? So, the reality is that our operational data is a moving target. That's a reality, right? It moves together with the business. And we have a high coupling with it. And we've also made a weird assumption. Like, we've made an assumption that data will forever be relational, and that's no longer true. The other problem is, at this point, we probably have enough data, enough databases, enough use cases that cool script that we build in a language that we can't maintain, well, we can't maintain it. And now we need to think about what's happening next, right? What is the next paradigm shift that we need to address? And this is where the next paradigm shift happens. So to kind of sum up, what do we have at this point? So we understand that our business and the architecture of our operational systems is moving away from relational data to non-structured, semi-structured data, right? The scale also increases. Right? The data is big enough that all kind of these ad hoc scripts that you just can't work with those. You need to start taking your analytical data plane seriously. And this is the part where you go to meetings and the term big data starts being tossed around liberally, right? And also conversations about maybe we need a data engineer here, maybe a team of data engineers, maybe a data analyst. And that's an interesting pivot point because that also means that we're creating a transition in our company of the type of people that we have that want to play around with data. So far, who played with the data, right? So it was people from marketing, the product manager, or boss. But now at this point, we might have people that, like we said before, data professional, their core responsibility is around playing around with data. So that can be a data analyst working together with higher management to make decision making. If you're working in a cybersecurity company, that can be a security analyst going through security logs. In other companies, they're going towards the world of machine learning. They might have a data scientist, those guys that speak all kind of weird languages, especially Python. And what's The same for all of these people, all of these data professionals. They do not care for your pre-aggregated data in your data warehouse. They want the data raw. They want the data as similar as possible to the source. They want it in high fidelity. And there's a really good reason to why they want that. They do not know what are the questions that they need answered, at least not right now. So if our salespeople know that they need to answer a specific analytical question right now, we will know that usually they ask based on geolocation. So we'll build an aggregated table based on geolocation. If I'm a data scientist and I will need to build a predictive model that I only thought about right now, and to train it I need data from 5 years ago, that means two things. One, I have no idea what data I need. And two, I need 5 years worth of data. And that all leads to the data lake. Who here heard the term data lake? Great, great. I hope some of you are the people that were in David's talk before. So before we delve into what have we changed in this architecture as a concept, right? For those of you that didn't raise their hands, what do we want to do? We want to create a place where we can store data, ideally indefinitely, in huge amounts, as raw as possible and in the highest fidelity as possible, as similar to the source as possible. Right? So how are we doing this? So let's kind of dissect what we've changed in this architecture. So go from left to right. So we've took our really cool, amazing script and we tossed it away. And instead, we brought an engine that can orchestrate and schedule data pipelines. So in this specific case, I put the logo for Airflow. If you're not familiar with Airflow, it is a very, very commonly used, almost the golden standard for data orchestrations. It's based on Python. It has a very, very rich community and ecosystem revolving around data. But essentially, that can be replaced by many other things like Prefect and Dexter, and the cloud providers have their own solutions for that. And in that, we will be writing new pipelines that their job is, again, to take the data from the operational data stores incrementally, once a day, once an hour, and copy them as is to our data lake. And that term is called an ETL. So an ETL stands for extract, transform, and load. Means we're extracting the data, in this case from our operational databases. We're transforming them, maybe add some more information, maybe change something, validate, or maybe we do nothing, right? Maybe there's no T. And then we load those. Where do we load those? We load those into our data lake. So what is our data lake? We want, again, to have a very, very simple, non-opinionated storage capability, right? Because we said the data is not necessarily relational, right? It can be many ways and shapes and forms. And we want it to be robust and economic enough that we can keep there infinite amounts of data. So what does infinite amount of data means? If we talk, for example, I work at Wix. In our data lake, we have 10 years worth of data. That is a lot, right? So we're talking about petabyte scales and more, potentially, of unstructured data. And ideally, like we said, we want it to be as cheap as possible. If we were to build this now, so for example, if we were to build this on-prem, if we're talking about more legacy systems, we would be using Hadoop HDFS. Nowadays, it'll be something more like mini IO. In a cloud environment, which ideally you would be in, if you're in AWS, you'll be using S3. If you're in Azure, you would be using either Azure Blob Storage or Azure Data Lake Storage. It's kind of hinted in there. And what we'll be doing, we'll actually be spilling the data there, again, once an hour and once a day, and never, ever delete it. And what are we going to do with it then? So the first thing that we're not going to do, we're not going to get rid of our data warehouse. Because all those people that we talked about before that need the data for analytical purposes, they still exist. They didn't go anywhere. And they don't know how to work with highly unstructured data sitting in a data lake. So we will continue to actually build the data warehouse for them. Ideally, maybe this is the part where we will reconsider if we're using the right technology. Because before, we kind of just took a database, slapped a script on top of it, and we ran everything. In this case, we'll probably think about maybe doing something that's more oriented towards that, right? So again, if we're working in a cloud environment, we'll be talking about things like Snowflake and Redshift and BigQuery, right? Every cloud provider have their own solution. But that can technically still be just a SQL database. But then we need to talk about our data professionals. And what are our data professionals going to be doing? Because unlike a database like a SQL Server that also has the engine, the data lake is kind of just dumb storage. Well, not dumb, but it's storage. So we'll need to give them the tools to process this data, and we want them to process it at scale. And we actually separating, in this case, the storage side from the compute side, which is a very powerful concept. And then we'll be actually doing analysis on this with highly distributed computing systems like, for example, Spark or Flink, or if we're talking about things that are more query-like, Apache Trino, formerly Presto, which again, those are engines that are highly distributed, that distribute very well horizontally and are able to do manipulations on vast amounts of data, even in an abstraction layer of simply writing a SQL. And lastly, we'll have our fun friends from the data science, and they'll be doing their machine learning, which again, we'll be using the same tools, but on top of that, they will be slapping all kinds of machine learning pipelines to actually take the data, turn it into inputs into models, and use that to train them, and then later do predictions, right? So again, very, very sustainable architecture. Many companies actually wish to be here right now. It works well when you have a lot of data. To a certain extent, of course, but there are problems with that, right? Like always, there are problems with this. What are the problems in this architecture? Another real question while I'm sipping water. Data loss. It's a good point. We'll talk about it in a second. More computing power, right? It's expensive. It's expensive. Data is expensive. That is actually true. That it continues to get expensive, right? The compute becomes cheaper, but you get more data, so it continues to be expensive. Sorry? No structured data. That is actually also a good point. So it's slightly true, right? Because in the data warehouse, we'll continue to keep it in a structured way. So the data warehouse would usually be fully structured. But you're right. So for example, the data we have in the data lake can be potentially not structured, and at some point, it'll be a mess. And we'll talk a little bit later about what that means. So I'll take a few of the things that you talked about right now and something that was said before. Let's start from the beginning. We talked about data loss. Why would we have data loss here? And this is kind of interesting because you need to understand how these pipelines work. So imagine that I have some sort of a database, and periodically, once a day, I'm going to run a pipeline that just says, OK, give me all the data, new data or updated data from yesterday. You take it, you copy it, right? Simple. Maybe you can run it once an hour, but it's still pretty much the same. And now, that works well if you're working based on standards. For example, you never delete data, right? You only do things like logical deletion, right? You put a flag that says the data was deleted, and you update the date that it was updated, right? But how many times have you seen people work exactly by the standards, right? The reality is things happen. People will delete rows of data from that database, and there's actually no way for that pipeline to pick it up. And that what essentially means is that the data that we now have in the analytical plane is diverging slowly from the data that we have in the operational plane. And if we're using that to make decision making, that's a bad idea, right? So that's just one of the problems that are actually involved in losing sync between those two sides of the same brain, right? The other part, and this is kind of sad to say, running batch operations, right? Running these pipelines incrementally, once a day, once an hour, still suck. Now, why does it suck? It sucks specifically when scale increases. To give you an idea to this, and this is something that happens a lot, you can have a pipeline that copies the data from the last day and you run it once a day. That makes sense. But what happens if that pipeline, because it does some sort of computation, runs for 12 hours? It runs for 12 hours just in order to copy and manipulate data from the last 24 hours. And then it fails because things failed. And then you need to run it again. So obviously the people downstream from you that expected this data, they're sad. Right? They need to wait another 12 hours to actually do something with this data, and this kind of have a chain effect sometimes. But if it fails again, guess what happened? The day ended, right? Now you are in debt of another day. And this is not a joke. This is actually a reality. And a lot of companies and data teams find out about this when it's way too late, right? They reach the point where pipelines run for 10 or 11 hours before they realize they need to make a change. So in terms of scale and recovery, batch pipelines still suck. And the last one, and that has to do with what the gentleman there said before, data latency. So we said we're copying the data once a day, maybe once an hour, and that's fine. That's fine if it's for reports for our boss, if our data science team are building machine learning that are models that are run once a day, and they run over historical data, and they run once at a time. But what if we want to build real-time machine learning models? What if we want to have real-time analytics? Because in the world of data, time equals money, right? Being able to reach these insights faster has a dollar sign on it. So all of these lead to the next paradigm shift, and this is a pretty big one. It's a pretty big one. So let's kind of see what we talked about, right? So the first one is data latency is unacceptable anymore, right? So we want to go from data being available for analytics a day or an hour to ideally seconds or worst case minutes, right? As near real time as possible. Usually what happens at the same time is also scale increases, right? So we're getting to the point where our batch-oriented processes don't scale anymore, or at least some of them don't. And also, this is usually the time where, again, the business moves. The operational data plane moves. We get more and more data sources, and integrating those into our pipeline, into our data platform, is becoming harder and harder and more intensive, right? So we need to start thinking in real time. We need to start thinking in data streaming. The problem with data streaming is that what you have written as a job, as a pipeline that needs to run once a day, once an hour, usually translates very poorly into streaming. And that means that many companies that reach this point, like little Yoda is saying there, need to rewrite almost everything. So a really big one, really big one. And this leads us to the real-time data streaming paradigm shift. So in the center of this architecture is our streaming engine. In this case, I've placed Apache Kafka, who is it's kind of the de facto engine used today, but there are other alternatives. So for example, if you're working with Azure, that's Event Hub. If you're working with AWS, that would be Kinesis. There's many, many more. But we'll talk about Kafka just in this specific example. And what is Kafka? For those who are not familiar, who in here knows what Kafka is? Okay, it's about half of the room, right? And by the way, there's a really good reason to why many of you would know Kafka. Not necessarily from analytical data. It's because Kafka is becoming a staple also of operational data architectures. Because as scale increases, that doesn't only affect analytics, that's also affecting our operating systems. And many, many teams and companies are moving slowly towards event-driven architectures because of that. And the event-driven architectures are also powered by streaming engines like Apache Kafka. So what is Apache Kafka for those that are not familiar with it? It's essentially like a highly, highly distributed log, or you can think about it as a queue, that enables mass amounts of data to be written by producers, and then have that data consumed sequentially by consumers. And it is horizontally scalable, right? Simple. Data is, if I capture a piece of data, I can write it, and it's available for others to read, ideally within seconds, right? Very cool. Now, how are we going to get the data into this amazing streaming platform of ours? So let's start from the left-hand side, right? The first option, which is kind of awesome at this point, is if my operational data architecture, or my operational architecture, already uses Kafka, because I have microservices that are communicating between them using Kafka, using events. And maybe we're even writing things in a domain-driven way, so those are domain events, right? They have a really good meaning and semantics. I can just simply plug in and consume that data directly. Right? It's super simple. I don't need to go to the database. But let's say that I do still want to go to that operational database. What I can do is I can tap into a thing called CDC. Anyone here familiar with CDC? Yeah, got some hands. So for those that are not familiar with CDC, CDC is a standard implemented by most common databases, short for change data capture. And what essentially it means is that for every change that happens for data in that database, an event will be emitted. So for example, I create a new row in a table, a new event says, new row created, here's the data. I update a row in the database, it says the table row updated, here's the data. I delete the row, even though I'm not supposed to, guess what happens? An event emitted says, row deleted, this is the row that was deleted. And what we can do is we can tap into this and stream those events into our streaming platform. And before we talk about what we're doing with this data, it can give you a hint to how this solves many of our problems with having the two sides out of sync. Because again, now changes just can't slip, right? The database is reporting to us what happened. And if we're connecting to the actual microservice, well, that's the actual system, right? So that solves for our out of sync problem. Now, we have all that data being streamed now into our streaming platform. Now, what are we going to do about it? So now we need to get the data into the destinations that we want them in. What we usually call that, we call that a sink. So if we're talking about Kafka, we will be using something like Kafka Connect. I didn't say, but for CDC, for example, we'll be using something like Debezium. Debezium is like a common framework for plugins that can consume that data from databases and pushing them into Kafka. And in order to sync this data, we will use something like Kafka Connect, which is a plug-inable infrastructure from the house of Kafka and Confluent that can stream the data into designated sources. So for example, if our source is our data lake sitting in S3, we can set up a connector that would just capture those events as they come along, maybe transform them, maybe not, and then just start writing them down into storage, right? And what that means is that, again, we're reducing latency. Potentially, we can get to the point where an event happened, and that data is now available in our data lake within seconds, maybe even less. And at this point, also, some companies start thinking about how the data is structured in the data lake, because in order to stream data into storage in an efficient manner, you need to maybe use a little bit more muscles, and that's where a lot of the columnar storages come into play. For those that were in David's talk, you probably know more about this, and more higher level abstractions for tables on top of storage layer like Apache Iceberg or Data Lake, but I won't go into that too much. And we can also potentially stream the data directly into other systems as well. So if we're using a data warehouse that is cloud native, many of those already support connectivity to streaming pipelines out of the box. So for example, if we're using Snowflake, we have Snowpipe. You can just move the data directly into the data warehouse. You don't even need to have an additional hop on the way, which is kind of cool. But we have actually done something interesting here besides reducing latency. But to talk about this, we need to talk about a term called polyglot. So the term polyglot, to those that are not familiar with it from the English language, means something that has many languages. A person can be polyglot, speaking in many languages. A document can be polyglot, has many languages. In the world of data, that means data or data architecture, which contains the data in multiple persistent ways. And this is not a new term. This is a term that was coined by Martin Fowler somewhere around 2005, I believe. And it sounds wasteful, right? Because we were taught that data is a very expensive thing, storing it is very expensive. Why on earth would you store it in multiple places? That's just wasting money. But in modern data architectures, we understand that we can actually not do everything that we want in one storage space, right? There's many, many conflicting things. So we said we want a streaming platform. That's a type of storage, right? Kafka is a type of a data store, sort of. And we need that to have the data available immediately for multiple consumptions. But we also want to have the data available infinitely, right? We can do that in a streaming platform. So for that, we have the data lake. So we might as well have it in two places. And that actually can lead to interesting things, like, for example, Lambda architecture. Who here is familiar with Lambda architecture? OK, so what is a Lambda architecture? Lambda architecture is what happens when you have the same data, or very, very similar data, existing in both a fast lane and a slow lane. So in our case, we have our data in a fast lane over Kafka, right? And it's available for immediate consumption. But it's also available in a slow lane, in a slow layer, in our data layer, in our data lake. And there it is stored infinitely. And there we can run relatively cheaply very, very complex computation over a long period of time. Now, what does that enable us to do? Imagine for a second that what we're streaming through our system right now is user behavior, right? So our business is we're tracking user behavior for whatever it is, user experience, security, whatever, right? So every behavior that a user does, any click that a user does is being streamed through our platform. And we have it in Kafka, have it in a streaming platform, and we also write it into the data lake. But we've also been doing that for the past year. So that means that our data lake also has everything that all of our users have done for the past year. And we can run very cool computations on top of that. So for example, we can analyze historical behavior for some users, right? So we can run a very complicated process on top of our data lake once in a while to check who are the users that have done A, B, and C. And then we can have this data cross-referenced in near real time with what the user have done right now. So if I want to say, if the user clicked this button and he've done A, B, and C for the past year, let's do something cool, right? Let's send an email. Let's raise an alert, right? Security system. Maybe we identify the user as a fraudster. Maybe this is actually taps into a machine learning model that uses the historical data as input and the real-time data for reference, right? So we're actually joining real-time data with historical data, right? So that is one very good example for Lambda architecture, but specifically for what you can do with polyglot data. But it doesn't stop there. So this is a really simple example of a fast lane and a slow lane. Another one to give you kind of an intuition of what that means is, let's say that we need to have over our data some kind of free text search capability. So none of these actually knows how to do that, right? I mean, technically you can work very, very hard to do that over your data lake, but there are data stores that are meant to do that. There are engines that are meant to do that. For example, Elasticsearch, OpenSearch, Vespa. So essentially what you can have is downstream to all of this architecture, you can stream the data also into a search engine. It's the same data. Now, maybe you won't have it there infinitely, but you'll have enough there so you'll have free text search capability. Now, why not just have the data there? Well, it's very expensive. We can't actually use that to keep infinite amounts of data. This is also not a really good place in terms of how it works for things like machine learning and analysis, right? It's good at a very specific thing, free text search, and maybe a little bit of aggregations. So having the data duplicated in another data source is actually a practice that's common in modern systems, and it's kind of counterintuitive for many of us. Now, what's interesting about this is all made possible by the fact that introducing a streaming platform into the center of our architecture is actually making our data very interoperable, very portable, right? Again, Kafka or most of the commonly used streaming platforms are ubiquitous. They have a huge community, both in the analytics world and the operational world. And that means that this enables us to actually plug and play much faster a lot of the systems that we want, new outputs for data, new inputs for data, right? It's highly interoperable. And what this also usually causes is an influx in the requests for introducing new data into your analytical platform, because people start to realize the potential in this, because we have shortened the distance between our operational plane and our data plane. And then what happens? You know, you probably have at this point a data engineering team, and then you come to them and say, I want you to plug in my new microservice and its data. And they say, oh, awesome, open a Jira ticket, it'll take 2 weeks. And at some point you realize that your data team or data teams is becoming the new bottleneck for the organization. So you need to optimize. So how do you optimize? You take your data engineering team, all those awesome people that know how to work and manipulate data, and you introduce them to another team, your DevOps and SRE team. And what that team knows how to do is automate. And that is what you do. So you're essentially taking all of that knowledge, all of that information that you have about building data pipelines, and you're automating them. So ideally, you can set up new pipelines instead of days and weeks, ideally, minutes. And again, this is a very, very sustainable architecture. So many companies aspire to be here. Many companies are working today very, very hard to be here. Maybe they were in the previous paradigm shift. Maybe they're still stuck there. Maybe they're just building something new. But if you are big enough, you will find out that this is not enough as well. And I do mean big enough, right? So again, I keep talking about what is a sustainable architecture. And like I said, that was a sustainable architecture. But at some scale, at some sizes, at some companies, that's not enough. And I'm not talking just about the huge companies, about Meta, about Google, about Microsoft, Amazon. It's also happening in slightly smaller companies like Wix, right? Not that small, but fairly small relative to them. And these are companies that have decided that they are going to be data-driven, or whatever that means. Anyone here works in a data-driven company? Okay, some of you. Anyone knows what data-driven means? Less hands, awesome. So it's a term that's being interpreted differently in different companies, and I will admit Wix is also a data-driven company. But essentially what we try to do is we try to turn data into a currency inside the organization. We want everyone to make decisions based on data, and that has a meaning. So that means that if we talked about before, right, at the beginning we had those data consumers, right, those product managers, salespeoples, your boss, and then we transitioned to the data professionals, right, those data engineers, data analysts, data scientists. Now the consumer for the data is everyone. Every single person in the company should have the ability to consume or maybe even create data. And at this point, the term big data kind of gets a new meaning. We don't count things in petabytes anymore, or hexabytes, or whatever bytes. We count scale by number of people manipulating the data. We count scale by the number of data assets, data products that exists, right? Tables, streams, pipelines, reports, analytics, all of these, right? And at this point, this is also usually the time where companies realize that you need to start thinking not in terms of data engineering teams that create the data. You need to think in terms of infrastructure, in terms of platforms. And this leads into what I personally define as kind of the modern view on a data architecture. And it looks super simple, right? We just added like a couple of things here. Yeah, what is he talking about? But again, what did we talk about, right? We want everyone to be able to use the data. The term, the buzzword that's being used for that is democratization, right? We're adding politics into architecture above all. But what does it actually mean? It means that we want self-service ability to create data assets, right? So ideally anyone, or at least people that are enough technically savvy. And we want everyone to be able to consume this data. And in order to do that, we need to add layers and layers of automation that are able to do all the things that we've done so far in a super, super simplified way. Because if before I had a data engineer, and that data engineers know exactly how to build a data warehouse table, and how to connect that into the BI tool, so later an analyst can analyze that. How do I automate that so anyone can do that? So in the world of data creation, this is kind of how I personally envision data platforms, or this is how I envision the data platform that we have at Wix. And I envision it as an iceberg. Now, I'm not envisioning it as an iceberg because we use Apache Iceberg, the technology. I envision it as an iceberg because what most people experienced or see are just the top. Those reports in the BI tools, those machine learning models that just kind of works. Maybe services, APIs that fetch all kind of very, very complicated data that later is being used by systems. But the reality is that there's infinite layers of complexity beneath them. And if we truly want to democratize them, enable everyone in the organization to do those, we need to think how to simplify those, how to turn those into self-service. So we need to think about how data is being ingested. How do I get new data into this platform? How do I store it? Where do I store it? How do I make sure that the person that's going to be creating a new pipeline doesn't even need to think about the fact that our data lake coincidentally sits on top of S3 or Azure Data Lake storage and is written in a specific columnar format? How do I abstract all of the processing engines, the complex processing engines sitting on top of that? How do I automate real-time stream processing? How do I automate the creation of batch processing? Because we're still going to have batch processing at this point, right? We're just adding stuff for creating those data warehouse tables. So it's very, very complex. But essentially, even if we've figured all this out, and believe me, not everyone has figured all this out yet, even the biggest companies, we've created a different problem. So this is a quote that I really like by DKM. DKM is a very famous science fiction author and software engineer. And it says, you can have data without information, but you cannot have information without data. Now, it's kind of a tongue-in-cheek, right? Makes sense, right? You can't, right? But we are in the world where anyone can create data assets. We have tens of thousands of tables, of pipelines, hundreds of thousands. How am I going to find what I am looking for? And this opens up a world called data management and governance. And it is a world in flux. These are new problems. These are problems no one needed to solve, at least not in this scale, 10 years ago. Because now we need to understand just the basics. 10,000 tables. How do I find the one I'm looking for? How do I create a catalog? But not just a catalog. I need to create user experience where anyone can find the data they're looking for. How do we do quality in scale? Right? We're thinking about software quality, but what about data quality? We need to figure out things like lineage, the dependencies between tables, because I have one table and I use it to build another one and another one. And what happened if this one failed? How do I traverse that? But then on the other side, there's the less fun stuff about data. Data can be very scary. Data can have very sensitive information. It can have information of our users. It can have private information. There's a lot we need to consider with everything that has to do with security, with governance, with the law. And if you think that is simple, you might have not read the news this week. Who here didn't see this article before? Meta have received, we have a guy from Meta here, I'm sorry. It's not coming out of his pocket, it's fine. Meta have received a 1.3 billion euro fine on GDPR and are asked to terminate data flow in Europe within 5 months. That is Meta, right? The company that should have all this figured out. GDPR is not only for Meta. It's for all of us, right? And that is just one specific type of regulation, and new ones are coming along all the time. So it's very complex. It's very complex figuring all this out at scale. Now, we can't talk about data architecture without mentioning the data mesh. Who here heard the term data mesh? So it's a relatively new term. It was coined by Zhamak Dehghani, roughly 2019. And it is an architectural concept as much as it's an organizational concept, because in many companies today, the way data operations were formed are very central. You can have a very big company, and within it, there's a really, really big core of just those people that know data, right? And even if you're democratizing everything, you still have this very strong core of people. And the idea of a data mesh is decentralizing all of that. So the same as we've decentralized to many extent the responsibilities of SREs in companies and DevOps in the past decade, the same way we want to decentralize the responsibility and ownership over generating data assets. Essentially, what we request is for our domain teams to be providing data as part of their offering. It's part of their responsibility. And the only way we can do that is by having all the stuff that we talked about before. We need to have strong capabilities of data discovery. We need to have strong capabilities of governance. Otherwise, none of that works. But we also need to have very high level of automation so those teams can actually build all this without this being their primary objective. So that's data mesh. Now, we have about 10 minutes, so it's a good time to talk about, what's the future. Right. So we talked about all the paradigm shifts that a company can go through, that an RD team can go through, but it kind of begs the question of, okay, fine, I understand, but okay, what's the next one? because we talked about evolution, right? Let's think about what's the next step to evolve to. So let's take our crystal ball and try to see what is in the future. Okay, I guess that was unavoidable. Yeah. So yeah, it's really hard to talk about the future today without talking about AI. Is it going to save our lives? Is it going to destroy our lives? Maybe we shouldn't be building data architectures anyway. We're all going to die. Jokes aside, AI actually has a very important impact on data, on the two sides of things. On the side of data consumption, we have seen in the past months large language models like ChatGPT, given the ability to generate code running on a sandbox and access to data samples, being able to perform as good as a junior data analyst. That is scary. And it kind of raises the question of how are we going to be interacting with data in the future? Are we just going to be asking it questions? So where is all the layers of SQL that we got used to going to go to? All those ancient BI tools of drag and drop, and where is all this going to go? People's expectations are going to be very, very different because the rest of our world is going to be transforming. So what's happening to the world of data? But this is also true for the data that we bring into our systems. These large language models work on highly, highly unstructured data. Human language, images. So we'll need to have all this data contained, but also managed in a way that later can be translated into the language of the machines. Things like semantic vector databases for embeddings are becoming crucial just to build like a small application using all these models. These are going to become essential parts of data architectures for systems that would want to tap into that. So, we got AI out of our system. Let's assume we're not going to die. What else is in the future? So a lot of this is things that we're seeing the hints of right now. And the first one is understanding that data is becoming part of our product offerings. Right? This is especially true for businesses that are building products for other businesses. Because while those customers are becoming more data savvy, they're becoming data driven, they require the same from you as a service provider. And that means that in order to keep an edge, a business edge, you can't just give a super good SaaS product. You also need to have super good analytical data. And that actually creates something interesting. It's like an arch. We talked about data meshes, but this is an arch spanning much more than your organization. That spans multiple products, multiple organizations. But what this also means that everything we show right now, if now that lands on the customer, what does that mean about SLAs? What does it mean about the guarantees that we give to our product? This is no longer, just for us, for our reports, for our decision making. This is what people are paying us for. The other thing that's happening is the commoditization of data services and data platforms. So this is the State of Data Engineering 2023 from Treeverse. It was published a couple days ago. So thank you, Treeverse guys, for letting me use it. And this just shows you the ecosystem of companies and open source projects just in the world of data engineering as they are as of today. That is insane. If you span this also further into the world of machine learning and AI and broad analytics and the infrastructure to support them, it looks like this. Right? So this is FirstMark's version of the 2023 state of ML, AI, and data. That is bonkers. This is an insane amount of companies trying to solve all of the problems that we talked about today, and some of the problems we didn't realize exist yet. And within these companies, through the creation of new value and through mergers and acquisition, new companies are forming and creating complete end-to-end data platforms. They're essentially giving the ability of building the things that only the mega brands were able to build for themselves to small companies. And this is happening in the cloud providers, if it's S3, if it's AWS, if it's Azure, if it's Google Cloud, but it's also happening by non-specific cloud vendors like Databricks or Snowflake or Starburst. So this kind of leads to the question of, wait, so you said data mesh, right? So the teams are going to be responsible for creating the data, got it. Okay, so the data is actually going to be part of our product offering, so essentially, is it part of our operational system at this point? I don't understand. And wait, we can just pay for all of this infrastructure? We don't need to actually build it? So what is a data engineer? What is the job of a data engineer in this world? And this is kind of an interesting thing because a similar thing have happened for the past decade in other roles as well. Things like the DevOps and the SRE role. And we're starting to see the divergence of that spectrum of data professionals that we know today starting to slowly open in places where, this is just automated. No one actually needs to build that. And we're finding people on this side of the spectrum working more on the business aspects because, well, for now at least, AI is not smart enough to understand how our business works in order to know how to model our data. Or maybe it is. And on the other side of the spectrum, we have the people that know how to build the infrastructure, how to make it scalable, how to make it strong and robust, or maybe at least integrate those commodity tools into the existing infrastructure of the company. But what's happening to all the people that are here in the between, the data engineers, or maybe data professionals in general? So these are obviously questions that I don't know the answer to. But we need to go back to the beginning. Because we started here. I'm putting the crystal ball aside for a second. Let's hope that there's not going to be any AI apocalypse in the next 5 minutes. We started here. We got very, very complicated. And that kind of raised a question, like, do we actually need all of this? And it's a very valid question. I use the term, this is a sustainable architecture, multiple times throughout this talk, and I truly meant it every step of the way. There's no silver bullet. There's no one architecture or one way that teams and companies should be building their architecture based on. What is right for you is what's right for you. This is just a way for you to maybe get a better intuition into the next time when you want to evolve this, how's the next paradigm shifts going to look? That's the future of your data. Thank you, guys.